Hi everyone, welcome back to Dave's Math Channel. I'm your host David Tare, and this is my fourth video in a series on limits, sub-series of calculus. And today I'm going to talk about one-sided limits. And I think this video is going to be kind of short and sweet, at least compared to the video I made yesterday on limits involving the epsilon delta definition of limits, which is very complicated. This one's going to involve it too, but since you've already seen it, it won't be too much different. Anyway, so let's get started. So let's first define what a one-side limit is. There's two types of one-side limits. They're called right-hand limits and left-hand limits. So we say f of x has a right-hand limit L at x0, and we write it as x as limit as x approaches x0 plus, that means x0 from above, of f of x equals L. And then that's true if whenever x is between x0 and x0 plus delta. So notice that now x is strictly greater than x0. We weren't requiring this before, but it's greater than x0 and it's not it's less than x0 plus delta. So if you can think of it, it's sort of half of the interval that we were talking about last time. It's just the interval from x0 to x0 plus delta. So as long as x is in that interval, then it has to be true that the absolute value of f of x minus L is less than epsilon. That's what we had before. So it's almost the same definition. It's just that we're only looking at one side. Hence the name one-side limit. If it's a right-hand limit, then x has to be on the right of the limit. And similarly for left-handed limits, it's almost the same definition. This time you write as limit as x goes to x0 minus. That means x0, it approaches x0 from below. The limit of that, of f of x in that limit is equal to L if for every element, every positive real number epsilon, there's a positive number delta, such that this time we require that x is less than x0. It's between x0 minus delta and x0. So it's the other side of the interval, if you like. If that's true, then again, we have to have the absolute value of f of x minus L less than epsilon. So those are the definitions of the the right hand limit and left hand limit, which together are one-sided limits. So that's how we define them. Very similar definition for general limit. And I'll just show you one example this time. So here we have a function that's shown on the right, and it's a discontinuous function. This has what's called a jump discontinuity at x equals 2. There's different kinds of discontinuities of functions, and what's interesting is that we usually use a two-sided limit if we want to prove that a function is continuous at a given point. Well, actually, a function could have a jump discontinuity, meaning it's discontinuous. In this case, this function is discontinuous at x equals 2, and yet it still has well-defined left-hand and right-handed limits, as we'll see. So in this case, we want to find the right-hand limit and left-hand limit of f of x. Well, let's start with a right-hand limit because that's easier. Notice that this function is linear on the right. It's actually quadratic on the left and linear on the right. And you can see the definitions. It has two definitions depending whether you're to the left side or the right side of the jump discontinuity at x equals 2. So if you're on the left side, it's defined to be minus x squared plus 6. And if you're on the right side, it's defined to be x minus 1. So that's how we define f of x. And as you can see, like I said, it's discontinuous. But now we want to find these limits, and we usually we use what the obvious choices in this case. If you just look at the graph, it looks like the left-hand limit is 2 because y equals 2, f of x equals 2 as we approach x equals 2 from below, but it equals 1 as we approach from 1 above. So we expect that the left-hand limit, which I'm calling L here, is equal to 2, and we expect that the right-hand limit, which I'm calling R, is equal to 1. So now we have to prove those limits. Well, like I said, it's easier to prove the right-hand limits. Let's do that first. So again, we use the epsilon delta definition. We want to prove that the limit is 1. So we calculate f of x minus 1. I probably should have put an absolute value around this, but f of x is strictly greater than 1 for x greater than 2. So That's just if you calculate it using the definition, you'll just see that it's equal to x minus 2 for that case. So because f of x was x minus 1, we're just subtracting another 1, we get x minus 2. So now we just have to prove, and what's nice about this is that we're also looking at x minus 2. Remember, we want x minus 2 to be less than delta for some delta. Well, we already know a delta, epsilon. So the way we've defined epsilon, we want x minus 2 to be less than epsilon, but then if that's true, then it's automatically less than delta as long as we let delta equals epsilon. So that was an easy case to prove. It's easy for linear functions, just remember that. The right side's harder because on the right, I mean on the left side, the left limit's harder because on the left side, f looks like a parabola. It's quadratic, and it's harder to prove limits for quadratic polynomials than it is for linear ones. So, but anyway, we can do it. So let's just do it. Now we're looking at, remember we're letting x be less than 2. So we want, and we're assuming the limit is 2, so we want to calculate f of x minus 2. You can see that's going to be positive here because f of x is greater than 2 if x is less than 2. That's pretty clear from the graph. So if you calculate that, you're going to get from the definition, you're going to get minus x squared plus 4. Well, now we want minus x squared plus 4 to be less than epsilon. So now we can solve for x. So, if you do that, you're just going to get minus x squared is less than epsilon minus 4, which is the same as saying x squared is greater than or equal to 4 minus epsilon. And remember, and then we have to take the square root of that, so we get x, since x is positive here. Is that right? I don't know. X is positive because the domain is from 0 to 2. So x is going to be less than greater than the square root of 4 minus epsilon. And remember, we want x minus 2. So that's going to be square root of 4 minus epsilon minus 2. And that can be our delta. So we're done. We found a delta. Square root of 4 minus epsilon minus 2. And you can see that as long as epsilon is positive and less than 2. Is that right? Because less than 2 because that's the domain. As long as that's true, then this quantity on the right, which we're calling delta, is going to be positive. And so for every value of epsilon, we found a value of delta that works. So that proves that the limit, the left-hand limit, is equal to 2, as we claimed. So we're done. We've proven the left-hand limit and the right-hand limit are what we said they were, and they're different. And one thing about a jump discontinuity is you can define it. You can say that a function has a jump discontinuity at a given point if the left-hand limit and right-hand limit are different. That's a definition of a jump discontinuity. If they're the same, then the function's continuous as long as it's defined at that point. And I'm just going to finish here by talking about different types of discontinuities of real value functions. It turns out there's 3 different kinds of discontinuities. The one I just talked about is the jump discontinuity. That's the one in the middle. So the picture in the middle is an example of a jump discontinuity. And I just told you the definition. There's also what's called, the simplest type is called a removable discontinuity, I think they call it. So the function on the left, it's a linear function, except it's a little bit of a weird function because it's linear everywhere except at this particular value, a. So f of a is not equal to f of x for the rest of the function. It's not part of that line. It's above that line. So you're going to get the same left limit and left-hand limit and right-hand limit for f of x. It's just going to be, what the linear function should be at x equals a, which isn't equal to f of a because of this weird definition we've used. We call that a removable discontinuity because we could remove it if we wanted to, right? We could redefine f of x just so that it has the value equal to the limit. and make it a nice smooth function, a nice continuous function. So a removable discontinuity is kind of a discontinuity that shouldn't even be there. You could make the function continuous just by defining it in a different way at that point. Jump discontinuities you can't do that with because they have different limits from the left and the right, like I said. And then there's a third type of discontinuity. I haven't talked about this yet. This involves infinite limits. I haven't talked about infinite limits yet. But you'll see this a lot. I mean, hyperbolas look like this. Like the function f of x equals 1 over x looks like this. It looks like this is another hyperbola. Maybe it's 1 over 1 minus x. That's kind of what it looks like. So this thing has what's called a essential discontinuity, which means that the function isn't even well defined at this point, A. We can't define, I mean, we could define it. We could set it equals 0, or we could set it equal to whatever value we want. But why do we call it an essential discontinuity? I'm not sure where that name comes from exactly, but you'll notice that the limits to the left-hand limit and the right-hand limit, the left-hand limit in this case is infinity, plus infinity, and the right-hand limit is minus infinity. And as you know, we can't let the value of a function be infinity. I mean, if we're dealing with real value functions, infinity is not a real number, or nor is minus infinity. So plus or minus infinity are not part of the range of any real valued function. And that's why we call this an essential discontinuity, because there's no way we could possibly make this function continuous, either on the left side or the right side, without letting it go to infinity, which is not allowed to do. So anyway, that's why we call it, I guess that's why we call that an essential discontinuity. But that is a third kind of discontinuity, which means I guess I also have to talk about infinite limits. That'll probably be the topic for my next lesson in this series. But anyway, that's all I have to say for today. Anyway, thank you for watching. Long live math, and I'll see you guys next time.